Hi, this is Mr. Max. So I have a few questions on the applications of differentiation, basically two questions, and I'm going to try to break it down in such a way that it will be a bit easier for you to understand. Right, so the very first question, part A, so says the volume of a solid circular cylinder with a radius of r centimeter, that volume is equal to 250 pi cubic centimeter. Now we're supposed to show that the total surface area of this solid circular cylinder is given by that formula there. All right, so let me see if I can just maybe draw my cylinder. So this is a rough sketch, okay? All right, so this is my cylinder here. And the volume of the cylinder, and we know that it's a solid, which means that it's a closed thing, okay? The radius is r. The formula to calculate the volume, yes, so we know that the volume is equal to, is it 250 pi? So that's the volume. We are supposed to look at a few things. If you find the volume of a cylinder, it is given a formula, volume equals to pi r square h, because your h is the height, which is what we don't know, okay? But we are going to give this height in terms of our pi and r square. So just to write down what we have now, using that formula. So we know that the volume is equal to 250 pi. So I'm just going to bring in the volume on the side. So the volume is equal to 250 pi. Pi r square, but we don't know h. So if you make h the subject of the formula, that's 250 pi, you divide it by pi r square. Well, you're going to be left with eventually, and this is where the pi's, they cancel. So the height, therefore, is nothing but 250 upon r square. So now we know what that is in terms of our r. So the height is 250 r square. So now we know the height, right? We are now not really interested in that. We just had to use the volume formula in order for us to find the height. Okay, rearranging the subject formula. We're actually interested in the total surface area of the solid. So what we do know is that it consists of two circles. So this circle here on top, right? So that's like a circle. Okay, so you do get the idea. And also the circle at the bottom. So those two, the circle is, remember I'm now busy with the radius. So this is going to be 2 times pi r square. The 2 is the two circles that are closed, top of bottom. The pi r square, that is the area to calculate the formula for the area of a circle, since there are two. The CSA that I wrote here, that is the curved surface area. And if you were to take the curved surface area, think of this as a piece of paper, okay? And the piece of paper is actually going to be like the circumference. So it is whatever this height is, or this distance here, times the circumference. And now the circumference of a circle, because the curved surface area is that part, which is 2 pi r, because that is your circumference, and you multiply it by the height here, and that should be multiplied by the height. Okay, so let me just write it in nicely. So the curved surface area of this is ordinary level work that you are supposed to remember. So it's 2 pi r squared plus 2 pi r h. But we also know that from our previous work, our value of h, this one here, has been replaced by 250 r squared. So that means our formula is nothing but 2 pi r squared plus 2 pi r times our height, and our height is 250 r squared. So we're not really entirely done. There's something else that I want you to have a look at. Okay, just look at your r here and your r squared. So when you multiply those two together, you should be ending up with 2 pi r squared plus 2 pi, but now you have got 250 upon r, because like the square and that one cancel, leaving you with r. But we're not entirely done though. So my formula can still be cleaned up. So this is the surface area, the area, just to maybe write it neatly. So the surface area, well, that's a very horrible way of making that letter. Okay, so bear with me. A little bit better is 2 pi r squared plus, but now these two should be multiplied over, right? So this 2, so it's like numerator over numerator, okay? 250 times 2 pi, that's 500 pi over r. In fact, this is the formula that we were supposed to prove, and this is where we needed to end when we had to prove that. 2 pi r squared plus 500 plus r over r. Okay, so that is what the question said, show that the total surface area. So the important thing is, what you have to realize is you need to find the height, but you need to use the formula for the volume, and you need to know how to calculate the volume of a cylinder, and it's a solid, so the area is not going to be open, it's not having an open side, so you have to consider the area for both circles on the top and as well as on the bottom. Okay, so there is a second part to that question. They say given that S can vary, so let's just quickly write down what S is. So we know that S is equal to, well, it's 2 pi r squared, and then it's plus 500. Let's just go back and make sure. So that was 500 pi over r. 500 pi over r. So that is 500 pi over r. Okay. Now once you are told to find the stationary point, you have to differentiate with respect to r. And then you're going to let that equal to 0. So we're going to find the derivative. So I'm just quickly going to write this nicely as 2 pi r squared plus 500 pi r raised to negative 1 power. I hope you understand that, okay? So if I now do the derivative of that with respect to r, I'm going to have 4 pi r, okay, because you always take 1 away from there, minus, because negative times that, 500 pi r raised to negative 2 power, because you take away 1. So this can further be written, just to make sure, as 4 pi r minus 500 pi over r squared. And I know that this should equal to 0 from the information that is a stationary value. So we want to find the value of S. What will the value of S be if R is going to be varying? Okay. Right, so we said let that derivative equals to 0. So from here on, it's just a matter of doing a little bit of algebra work. So in order for me to get rid of the r square, I'll multiply here by r square, I'll multiply here by r square, and I multiply here by r square. So this leaves me with pi, 4 pi r cubed minus 500 pi, because the r squares cancel, equals to 0. So 4 pi r cubed is equal to 500 pi. Then r cubed is equal to 500 pi over 4 pi. That is making that the subject of the formula. Again, if I'm here, I realize something, and what I'm realizing is that the pi's they cancel. So what I'm left with is 125. And in order for me to find our value of r therefore becomes the cube root of 125, and r is equal to 5. Okay, so that's my value of r. So given that r can vary, find the stationary value of s. Okay, so that particular question, that is the method that you will be using in order for you to find the unknown value to that question. Right, so there is a part that says we are supposed to find not the value of r per se, but we are supposed to find the value of s. So once we know now the value of r is, as I said, r is equal to 5, we are supposed to calculate what the value of s is. Right, so the value of s will therefore be, now you need to substitute that into the original equation because we are looking for the value of s. We're not looking for the derivative. We have used the derivative when we said that equal to 0. So you're going to substitute that into our value of s. And this is perhaps here where I feel you need to take a calculator. Okay, right. So which I'm going to use this part here. So we'll just change the color. So the value of s will be, so this is what I'm looking at, okay? It's 2 pi, now it's 5 squared plus 500 pi over 5. So what is the value of s going to be? That is, remember, it's centimeter. So grab your calculator and that should give you some value. So I'm just going to bring out mine. Okay, let's just make sure that, so it's 2 shift pi times 25, I hope you 25, you see it's 5 squared, plus 500 pi, we're going to divide that by 5. My answer is about 471. Just to reiterate, we're probably going to leave it 0.23 something there, okay? 0.23 and so on and so on. So this is the value of pi, or of s, what we were supposed to find. Okay, right. So now we have that for part B because that is what we were supposed to calculate. Right. So we are going to go to part C. Determine the nature of this stationary point. When you are determining the nature of any stationary point, you have got 3 types of stationary points. You have the minimum, you have the maximum, and you have the point of inflection. On all these points, you're going to find the first derivative, you're always going to let it equal to 0. But now, in order to determine the nature of the stationary points, we need to take the second derivative because it will tell us something. And here's what the second derivative tells us. D square of s over d r squared. If that value is greater than 0, like a positive number, then the nature of the stationary point will be a minimum. if the second derivative is less than 0, okay, then the nature of that stationary point will be a maximum. So what is our first derivative? It's, if we bring it in, it's this particular value that I'm interested in, 4 pi r. So the first derivative is this value here, which I will rewrite as 4 pi r. So it's the derivative is 4 pi r minus, so just go back and make sure we have the correct value, minus 500 r raised to the negative 2, minus 500 minus 500 r raised to the negative 2 power. Okay, so that is the first derivative. Okay, that's the first derivative, ds dr. Okay, so when you do the second derivative in order to determine, so well, of course, this one here is our first derivative. So to do the second derivative, you say d squares over dr square should give you, now remember that's 1, so when you multiply, you're just going to have 4 pi. And when you multiply that with that, you get the positive 1,000, because 2 times 500 is 1,000, r raised to the power of negative 3. Okay, so this then can be written as 4 pi plus 1,000 r raised to the power of 3. If r is equal to 5, what do we get? So we have got 4 pi plus 1,000 over 5 cubed. We need to be able to see what number do we get. And if you substitute it in there, you're going to get some answer where, let's grab the calculator, perhaps. Let's just clear our display. So it's 4 times pi plus 1,000 divided by 5 raised to the power of 3. Okay, so let's hope it gives me. So it's about 20 point. Let's just have that small. Let's drag you here. It starts to play its games. Well, it doesn't want to do that. We simply 20.56, 20.6. So it's roughly 20.6. So it's about 20.6. Well, so what does this tell you? Well, we have got a value that is greater than 0. So when we are dealing with determining the nature of the points, so if the value is greater than 0, as we have seen, we therefore have a minimum value. Okay, so therefore you can actually conclude and say, wait a minute, the nature of the turning point is a minimum value, because the second derivative is gonna give you a value that is greater than 0. Okay, right, so we have got a second question. A rectangular tank is made of a thin sheet of metal. The tank has a horizontal square base and no top. This part, very important that you understand. So when a tank is full, it holds 500 liters. We are supposed to show that the area is given as this particular expression. So let's look at what we have. So a rectangular tank, and I should make this a little bit smaller. So the rectangular tank consists of, so let's suppose if I have my drawing here. So this would be my rectangular tank. It's not a perfect drawing, of course. We shouldn't hate. It's kind of interesting. So that's my rectangular tank. What we do know from our information, we know that the base is a square. So this is x. That's x. We know that the volume is 500 liters. You should do a little bit of conversion. You should go back to the facts that you know. You should know that 1000 cubic centimeter is equal to 1000 milliliter, which in turn is equal to 1 liter. Therefore, 500 liters is equal to 500,000 cubic centimeter. And the reason for that is because our answer, we are looking at volume. So the volume of a cylindrical tank will be this height that we don't know. You just multiply the dimensions. So it's x squared, that's x times the height. Now, we can find the volume is told, we now know the volume is 500. So if the volume is 500,000, okay, then the height can be written as 500,000 upon x squared. So this would be the new way for me to write the height. Number one, that's fine. So we now also know something else. We know that the tank is open here. Very important now why that information is going to be put. Because once we are now finding the surface area of this shape, we are going to take the area of the base, which is obviously that particular square. But we're only going to consider one because on top it is kind of open. So the area of the base, and you find the area by simply multiplying. So the area of the base, let's say base area, is nothing but x times x. Okay. Then let's make it a little bit thicker. The area of the four faces. Now it's quite important that you understand what I mean by that. So if I were to highlight, and let me just bring in a funny color. You see at the back you have got that face there, right? So that's the back side. That's the face that you have there. But you must be careful. You have one at the back, you have one in the front. So there will be four of these. It was that one there, which is one face. Then you have another one, which is on the side. So there will be two on the sides. There will be two. So the other one will be here, okay? And there will be two blue ones. So the other light blue one, if I have to go back, perhaps going to be the one in front here. So at the end of the day, we're going to have four of these rectangular faces. And the area of these four rectangular faces, okay, the area of them, so there will be four of them, it's x times the height, which is 500,000 upon x squared. Okay, so that's one face. We know we should have four of them. So 4 multiplied by 500,000. Now remember, in order for you to find the area of this, you just multiply the dimensions together times x. Right, so if you look at the bracket inside will give you 500,000 over x, because this x square and that one here will cancel, leaving you with x under. Right, so when you multiply out the 4, that means the 4 times that, you'll get 200, no, 2 million rather, upon x. Okay, so once we have 2 million over x, what you've just calculated, that is the faces of the 4 rectangular parts. Okay, we also have the base area, which we know is x squared. So the total surface area then, which we're going to write as A, should equal to that base area, which is x times x, which was x squared. Okay, it's going to be that x squared plus 2 million over x. Let's just make sure that this is indeed what they wanted us to prove. Okay, let's make sure of that. So let's go back. We realize, well, it's x squared plus 2 million over x, and that's exactly where we ended up with. Now, they are saying we're supposed to find the derivative, dA dx. So let me just quickly write that here. I'm running out of space. So A equals to x squared plus 2 million over x. So if you are finding now dA dx, you're going to take the derivative, is going to be, just maybe to rewrite this, it's x squared plus 2 million x raised to negative 1. It's exactly the same. I'm just writing it the other way around. Okay, so to derive this, you're going to have 2x minus, because that negative there times that, minus 2 million. Now it's going to be x raised to the negative 2 power because of that. Okay, so obviously this gives us the same as 2x minus 2 million over x squared. Okay, so we now have the derivative. Now we are supposed to find the value of x for which that derivative is equal to 0. So we can go ahead and say, okay, if the derivative is equal to 0, that means 2x minus 2 million over x squared should equal to 0. So from here on, it becomes an algebraic problem, which you should be able to solve by now, finding different ways. So I like to multiply by x squared so that the x squares can cancel. So what you do is you're going to have here 2x cubed minus 2 million should equal to 0. Of course. Well, you can also go ahead and divide this by 2 just to simplify the fraction. So you have what, x cubed minus 1 million will equal to 0. Okay? So you have x cubed, we're looking for the value of x, is equal to 1 million. Then x cubed is equal to 10 raised to the power 6. That's what 1 million is. And now you have to take the cube root of both sides, okay? Or you should know that 10 raised to the power 6 should be raised to the power of a third. That's another way of taking the cube root, okay? So if you take the cube root of something, is the same as raising that something to a power of a third. So ultimately, you're going to be left with x equals to 10 squared because 6 times a third, which means x is 100. Okay, so we now know, we now have determined the value of x. That's what they said. Find the value of x, so we have done that. Now there's a part that says show that this value of x gives a minimum value of a. So when we are told that it gives a minimum value of a, we need to differentiate to find the second derivative. So I'm just going to bring in this part, which was my dA dx. Okay, so 2x minus 2 million x raised to the, so let's just change this color. So we know that dA dx, so it's going to be 2x minus 2 million x to the power of negative 2. So it's 2x minus 2 million x raised to the power of negative 2. Okay? Just write that down. So when you do the second derivative, you're going to have, remember, that's going to be 2. And then that times that gives you positive 4 million x raised to the power of negative 3. I hope you are with me so far, and I hope that you are making sure that you don't get confused. I'll suggest that maybe you go back and then you play around with this and then you see what you get. Well, of course, I'm going to substitute 100 in there, but let me just write this as 2 plus, and that's 4 million x raised to the power of 3. So if x is equal to 100, so that should give me, to see what the derivative would be, so that's going to be 2 plus 4 million divided by 100 cubed. Right. So it's quite a heavy number here. So let's bring in our calculator just to be on the right path. Let's clear that display. So you have 2 plus 4 million. And we're going to divide that by 100 cubed. Okay, 100 cubed by a million. So we get an answer of 6. So if your second derivative is equal to 6, it means it is positive. And when that is the case, we are dealing with a minimum. Okay, so I hope you do still remember that. Okay, so this part of the question here had a lot of things in it. They say show that this value gives a minimum. You had to show by taking the second derivative, and you were supposed to find a positive value. And once you have a positive value, then you know that the derivative will therefore be a minimum. Now they're asking us to find the dimensions of the tank. Well, it becomes actually straightforward. So our tank, okay, as it was, so this was x, that was x, and our height. Now, it's very easy and straightforward for us to determine the value of x, since we know x is equal to 100. But the height was given to us, and this is where we need to go back all the way to our diagram. What is our height given? Well, it's 500,000 over x squared. And I also wrote it here when you're doing the equation. Our height, this is here, so our height is here. This is the one I'm referring to, 500,000 over x squared. So 500,000 over x squared. So the height, which is 500,000 over x squared. Now we know what, therefore, the length, it's interesting, spelling issues, length of the sides of the base is 100 centimeter, so that checks out. The height is 500,000 divided by 100 squared. Now remember, that's like 500,000 divided by 10,000 is 1, 2, 3, 4 zeros. So the answer will be centimeters. Okay, so we have our height, we have our length of the side. Okay, and surely that's it for these two questions. You have to come up with a drawing, and then you have to look at differentiation, and your algebra should be sound. Otherwise, you will have serious problems when you are dealing with this type of questions. Okay, I hope that was a little bit helpful, um, and it can assist you maybe to have a better understanding as far as that is concerned. I'm going to do quite more videos on the applications of differentiation.